1.3, more on functions and their graphs. So we're going to start here looking at graphs and finding where graphs increase, decrease, and have constant values. A function's increasing when your values for your y are going larger and larger. But when we list these intervals, we list them about the x. And I can't stress enough here, we will find these, it's increasing on an open interval. Okay, meaning we're going to use parentheses every time. We never close the interval when we talk about an increasing interval. The function is decreasing on an open interval. And again, it's the y that you're going to see decreasing, but we list the x values for that interval. And a function is constant, again, on an open interval where you remain at the same y value for a length of time. Okay, so as we list intervals, we look for the change in the y, whether it increases, decreases, or stay constant. But we list the interval in terms of the x, and that's something we have to work on. Interval is listed in terms of x, but it's actually the y value that does the increasing, decreasing, or constant. Okay, so let's look at number 1 here. I have a graph of my function. The blue line here is the function. I guess on your paper it'd be black, but in my notes it's still blue, so you can look here in my notes. I'm looking to say, is there any place where my y is increasing? Well, I notice from this point here all the way here and keep going, my y is increasing. So my increasing interval, and remember, my y is increasing, but when I list my interval, it's always an open interval, no matter what. It's always an open interval. And I'm listing the x values from where I see the increase. So I see the x value starts at 0 and continues on to the positive side, meaning towards positive infinity, while my y is increasing. So I'm just going to be 0 to infinity. Now I'm looking to see, is there anywhere on my graph where my graph is decreasing? So is there any place where my y's are decreasing, going down? In this particular graph, I'd have to say no. So I just put none. And then finally, I'm looking for an interval in which the function is constant. And again, that's my y values I'm looking for a constant. And I'm going to list my x values where I see them, if I see them at all. Well, it looks like all through here, this is constant. I have the same y on all of these. The far left side of that is my negative infinity, and I go all the way until I hit the 0 on the x. Okay, it's all about the x when I list these intervals. Okay, so I'm looking at the y to determine increasing, decreasing, and constant, but I list the interval by the x values it is between. Okay. All right, so the next one here, definitely more going on here, so we could have more than one part to our answer. So I'm looking for anywhere in my graph where my y is increasing, okay? Well, it looks like from here until I get to here, so I stop right there, it's increasing. Then it starts to decrease. Then from here to here, it's also increasing. So I actually have 2 intervals. My first interval looks like its far left is negative infinity, and it increases until I get to the x of -1. We always go with the x value. I also have an interval that starts at +1 and goes to positive infinity, and those are also increasing. Because I have 2 intervals and they're both part of the answer, I put a union between them. For B, do I have any intervals where I'm decreasing, where my graph is going down or my y value is decreasing? And it looks like it's between the 2 times when I am increasing. So it looks like it starts at the x value, of -1, and it goes to the y value of 1. And then I look again, is there anywhere where the function is constant, where it stays exactly the same value? And I'd have to say in this case there is none. Okay, so increasing, decreasing, constant, it all depends on what we're looking for the y to do the increasing, decreasing, or constant, but we list it by the x interval on where that is taking place. All right, page 2. Now we're going to talk about relative maximum and minimum points. Okay, obviously with a lot of these graphs, we get arrows on both ends, which means they go on forever, and we can't find an actual minimum point and an actual maximum point unless they stop. As soon as there's arrows, it never goes there. However, we can get these relative min or max points where the graph turns, okay? So as we see turns in the graph, we can get a value that's sorry, I don't know what I just pushed. I can get a value that's a relative minimum or a relative max, where it kind of reaches a point and then does a turning point, okay? So that's what we're looking for, basically, our turning points, and then saying, is that a maximum point relatively, or is it a minimum? Obviously, if you look at this relative max, I do have points that go higher than it when this arrow goes through, or this one goes lower than that relative min, but it's a point, it's a relative min or max, okay? Now, the trick on here is, how do we define these? How do we answer this? And you have to really stop and think what the question is asking and how it's appropriate to answer it. Sorry. So for A, it says, find the numbers, if any, at which f has a relative max, okay? This is looking for an x value where you see a relative maximum point, okay? So when I say, yes, I have a relative max, okay, that point would be at this x value of 0 and this x value of 3, okay? So those are my relative max points. But the second part says, what are these relative maxima or minima, if that's what it is? So now, what are these? I'm asking for the y. Now, the safest way to write these so that you are answering them in the safest place, I can say at f of 0, because remember, that's always my x. At f of 0, I have a relative max point of, and this one is also 0 because my y is 0. So this is my x, remember, and this is my y. And then in the same respect, I can do f at 3. When I go to my f at 3 here, it also has a relative max point of 0. So those are my relative max. Now, I can look for my relative mins. I'm looking to see, do I have a very low point? Okay, my relative min. It looks like I have one down here, halfway between 1 and 2, so I'm going to say at 1.5. So it's always the x value I say that has a relative min or max. And then if I want to give what that relative minimum is, I'm going to say f at 1.5 has a relative min point, it looks like, of -5. Okay. So moving on to the one at number 4, it's important to notice the arrows and where they're going on that one. So for A, again, I'm finding the relative max. Okay, I'm looking, is there a high point over there? So it looks like at x equals 0, I have one, and I can write this at f of 0. What is that max point? Looks like it is 2. Okay, or for B, if I do a relative min, if you notice down here, these both hit these points down here, and then they kind of look like they're going to go back up a little bit. So it looks like at -3 and at +3, I have a relative min. So if I write those, what are those relative minimum? At f of -3, it looks like I'm at -1. And at f of 3, it also looks like I'm at -1. Okay? So turning points, that's really where we're looking for these relative min and these relative max. All right, let's talk about even and odd functions. And I can't stress enough to you, we're going to start them here. We might see them very sporadically, but this concept will come up over and over and over in PreCalc. So don't forget these definitions of even and odd functions, because we will see this. Okay, I do want to preface this with, we have even functions, we have odd functions, and we have some that are neither. So it's not like there's two categories and you have to put each equation in one of those two. They can be neither. So that's something important to know. So if I have a function, I know it's an even function if I plug -x in for all my x's, and my resulting equation is exactly what I started with. Okay, so the function does not change. Okay, nothing changes at all, and it looks just like what I started with. Then I have an even function. If I plug in a negative x into everywhere I see an x in that equation, and my entire equation goes opposite what I saw, so the changes the sign on everything, then it's odd. And if there's a mix, some signs change, some signs don't, it's a neither. So remember, there are 3 categories, and it could be a neither. Okay, so let's try the first one. F of x equals x cubed plus x. So I'm going to plug in negative x everywhere I see an x. I plug in negative x into my x cubed. I plug in negative x into my x. I simplify it. What's negative x cubed? Well, a negative and a negative negative stays negative, so I get negative x cubed. What's plus times negative x? It's just negative x. Okay, I look at my function compared to what I started with. So when I compare this, what I just got, to what I started with, what happened to my equation? It looks like all my signs changed. Because all my signs changed, I have an odd function. Okay? So let's try it again on the next equation there, my next function. I'm going to plug in negative x into every x spot. So I get negative x squared minus negative x to the 4th plus 1. So here, negative x squared, that's 2 negatives, it stays positive. So I just get x squared minus negative x to the 4th, well, that's 4 negatives, and that stays positive, so I just get x to the 4th plus 1. So here's my final equation once I simplify it. Here's the function when I started. What happened? From the beginning to the end, I ended up with no signs changed. And because no sign changed, I have an even function. Okay. All right, third one. Square root function. Okay, it's a little bit different function, but we still do the same rule. We're going to plug in a negative x and see what happens. I plug in negative x into the squared, and the square root of 1 minus negative x squared. Well, negative x squared, that's 2 negatives. It still stays a positive, so I just get x squared. My 1 doesn't do anything, minus a negative x squared, again 2 negatives, and that just stays positive x squared. I look, there's nothing more to simplify, so I look at what I have compared to what I started with. Did all signs change, no signs change, or just some of them? It looks like no signs changed. Since no signs changed, this function will be even. Okay? And I'll admit, I didn't do one with neither, but be ready for that, because don't think it's an either or, that there's just 2 categories. You can have that third category of neither. All right, what if we're on a graph? That's what we're looking at here next. What if we don't have a function per se, but we see a graph? Can you tell even and odd from a graph? And the answer is definitely yes, okay? So the idea here is a little bit different, that when I plug in negative x, obviously if I had the equation I could do that and I could see if it's going to be even or odd. But the easiest way, an even function is symmetric with respect to the y-axis, okay? So here's my x-axis, here's my y-axis, okay? And when it's symmetric with the y-axis, basically means I can fold it on that y-axis. So think about maybe a parabola like this, if I could draw one symmetric, okay? If I could fold it right there and they look identical on both sides, then that's an even function, okay? An odd function is a graph when I plug in the negative x, I obviously get opposite the equation if I was doing that, or it's symmetric with respect to the origin, okay? This is a rotational with respect to the origin, okay? That's what you have to remember there. I don't know if I can even draw, I'm going to draw a rational function. Do you remember these L-shaped ones? Okay. So if I took this and I decided to take it from the origin and I decided to spin it, right? I move this and I spin it this way. If I spun it like 180, would it look like itself? And I think the answer is yes, it would. So because of that, this is what we call an odd function, because if I can spin it at the origin and it looks identical to what I started with, so the spin of 180 degrees, then yes, it is odd. Okay. So looking at our pictures on 8, 9, and 10, we're trying to decide, are these graphs even, odd, or neither even or odd because of how the graphs look. So on number 8, it looks like if I tried to fold it down the y-axis, no way is that going to look the same, right? So I'm going to just erase that. There's no way I can fold that. So now I'm stuck with, can I rotate it? If I took this right here and I rotated it, you can just turn your paper 180 degrees, flip it upside down. Does it look identical? If it does, you say, well, okay, then that has to be odd, right? It rotated. Okay, so for 9, I look at that one and I see the picture. This was actually one I used earlier, isn't it, for the other graph. Can I fold it down that y-axis? Would it look identical on left and right side? And I think we could easily say, yes, it does. So because of that, it's even, right? I can fold it right down that center line. Okay, so I get to the number 10 here. The question is, I have 2 options. Can I fold it down the center line? It is a parabola, but it's skewed to the left, so that's not going to work. Could I spin it? Can you turn it 180 degrees upside down? Does it look identical? I'd have to say probably not, right? So because of that, that's neither. So that you can see what this looks like algebraically. Does anybody recall how I can write the equation for this parabola? Okay, it's a quadratic, and I'm going to tell you, I'm going to write it off of the intercept form. I don't know if you remember that from Algebra 2, but I see that it crosses my y at -3 and 1. So if you just stop and say, wait, if that was factored, and I have a solution of -3, its factor must be +3, x plus 3. And if I have a factor of 1, its factor must be x minus 1. Okay, this is kind of the function it goes with. Now, the one thing I notice about this parabola, it's actually upside down. So I probably need to throw a negative out front to make it upside down. Okay, so let's go ahead and I'm going to leave that negative out front. I'm going to FOIL those. I get x squared. I get a -1x, a plus 3x. That makes a plus 2x in the middle. Plus 3 times -1 is -3. Okay, now I'm going to go ahead and throw the negative all the way through. So -x squared minus 2x plus 3. So there's my function that would match this graph, okay? Now, I will throw out there, there's a chance there's a multiple in there, it's kind of a scalar that stretches or shrinks it a little bit. But to be honest, to check the even and odd, that's not going to have any effect. Even and odd deals with the signs, okay? So I'm going to do a quick, and see if we can do this a little bit mentally. I'm going to throw in my negative. So if I throw in a negative here to -x squared minus 2 with a -x plus 3, there's nowhere to throw in a negative. Well, my -x squared, that's going to stay positive. So I just get -x like I had with a square. But my -2 times -x becomes plus 2x, and then I'm with plus 3. Does my new f of -x, does it match my f of x? Well, the first 2 stay the same, but that middle one changed, and the last one didn't change. So I had some change and some not change. So because of that, it's a neither, okay? So we look at the graph, and I can't fold it or spin it, so that supports the neither. And then when I look at algebraically, it also supports the neither, because some change and some stay the same, okay? So that's just a quick view, since we didn't have one earlier of a neither, and now you've seen one of a neither, okay? All right, let's keep moving here, and let's look at what we call a piecewise function. Okay, a piecewise function says I have a function, which means it can pass that vertical line test if I graph it all, but it doesn't have to be a continuous line, okay, or a continuous curve. There's pieces that fit different parts on the graph, okay? So on my first 2 here, all I want you to do is evaluate the piecewise function at the given value, okay? So what you see on number 11, it's considered one function, f of x, but part of it is 6x minus 1 if your x is smaller than 0. And then it's 7x plus 3 if your x equals or is larger than 0. So it depends where you go depending on what your x value is. So for A, it says f of -3. Well, what is -3? Well, -3 is less than 0, so I'm going to be on the top. Okay, that's the function I have to use this time around. So I take 6 times -3 minus 1. I get negative 18 minus 1. So my f of negative 3 is going to be negative 19. Okay? All right, my next one, f of 0. So I'm still in this same function. I have to choose, though, where is f of 0? Well, that's exactly 0. And I only see the equal sign here on the bottom one. So 0 equals 0, right? So I have to plug it into 7 times 0 plus 3. Well, 7 times 0 is 0, plus 3 is 3. So it looks like at f of 0, I am on 3. Okay? Make sure you don't plug it into the top equation because the top equation does not equal 0. It's only less than 0. All right. And finally, the last one I have is f of 4. Well, 4 is definitely bigger than 0, so I am going to, is going to be on the bottom equation, right? So I'm going to do 7 times 4 plus 3. So I get 28 plus 3, which is 31. So it looks like f of 4 equals my 31. Okay, so on a piecewise function, you choose which piece your x value matches, and then that's the piece or the part of the function you plug your value into. Okay, it looks like 12 is not very pretty, but we will work through it one at a time here. I'm starting with h of negative 5, and I see two ways. So if x equals 3, I plug it into the bottom. If x does not equal 3, I plug it into the top. That's my only limitations here. So x, it's negative 5. That's not equal to 3, so it looks like I'm going to plug it in the top. Negative 5 squared minus 9 over negative 5 minus 3. Well, negative 5 squared is 25. That's positive because the negative times the negative. Minus 9. Negative 5 minus 3 is negative 8. 25 minus 9 is 16 divided by negative 8. Looks like I get negative 2. So h of negative 5 is negative 2. All right. H of 0. Again, it doesn't equal 3, so I can go ahead and plug it into the top there. I get 0 squared minus 9 over 0 minus 3. So on the top, I'm only left with negative 9, and the bottom negative 3. So it looks like h of 0 is going to equal positive 3. Two negatives make a positive. All right. The last one, don't overthink it. It says, what is the function at h equals 3? Well, it tells us. If if x equals 3, then my function equals 6. So I just put equals 6. There's no work to do, okay? Now, quick note, why on the top equation can x not equal 3? Well, we have to be careful. It would make that denominator undefined because you're not allowed to have 0 in my denominator. So that's kind of why that is a piecewise function there. So they give you a different value there so that they could keep that function consistent or a value for it in every x value. All right, last page. Let me scroll up here. Couple fun things here. I'm going to graph a piecewise function for you because sometimes people struggle with what is a piecewise function, what does it look like, why does it do this, okay? I'm going to be honest, piecewise functions are the most popular in things like cell phone plans or even electric companies or things where they want to give you a deal. I think my credit card uses it. They'll give me like 5% cashback bonus up to $1,500 or something like that, and then they change the rates from there. So there's all kinds of things that they have, these introductory things they want to get you in with, and then after you meet a certain requirement, then the plan changes to a different requirement. And those are called piecewise functions, okay? So in real life, there's a lot of them, okay? So when you're graphing a piecewise function, we're just going to do t-charts here to do this. So my first one, I have two parts to this. I have f of x, and my first function is negative 1/2 x squared. And then on my second one, it's going to be 2x plus 1. Okay, now the question comes on a t-chart, what value should you start with? And I can't stress this enough. This value that you see on your conditions, that is where you want to start on both of them. Don't worry about the not equal to right now. You want to start with that on both of them. So I'm going to start both of these t-charts with 1. Okay, on the left with the negative 1/2 x squared, I need to go smaller than 1. So I'm going to go 1, 0, negative 1, negative 2. Okay, I'm going smaller. On the other one, because it's x is greater than or equal to 1, I'm going to go bigger than 1. 1, 2, 3, 4. But we want to use that same value on both of them, okay? So now we plug in. 1 squared is 1 times negative 1/2 is negative 1/2. 0 squared is 0. 0 times negative 1/2 is 0. Negative 1 squared is 1 times negative 1/2 is negative 1/2. Negative 2 squared is 4. 4 times negative 1/2 is negative 2. Okay? I'm going to graph that part of the graph. Okay? So I start at 1 and negative 1/2. Okay? And so at 1, negative 1/2, I'm about right in there in between. Okay, this is what's important. This was not equal to. Okay? So I want to be careful at that spot. I don't want actually a dot. I want an open circle. Okay? So I'm going to put an open circle at that 1 and 1/2. Okay. Then I go to 0, 0, negative 1 and negative 1/2, negative 2 and negative 2, okay? And it looks like this graph is going to keep going this direction. It looks like it's like a partial upside down parabola. Looks like it's going to keep going. And it is an x squared, so it should be a parabola. Okay, on to my second part. That's my second piece of this piecewise function. Plugging them in. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. 2 times 4 is 8, plus 1 is 9. Okay, I go to 1. Now, notice this time my 1 is equal. So I want a closed circle this time at 1, 3. So I go to 1, 2, 3, a closed circle. Then I go to 2, 5. 1, 2, 3, 4, 5. To 3, 7. And it looks like 4, 9 is going to roll off my graph a little bit, but I start at that dot and I'm going to keep going up to the right and I put an arrow that direction. Okay? So, there's my piecewise. You can tell there's a disconnect. Okay? But let's talk about the domain. Where does my domain start from? Interval notation, always for domain here. My domain, it looks like my farthest left value is negative infinity. Can't make negative infinity right now. Then I go all the way to, this is an interesting, I go to 1, which is not included, but then I also start at 1 and go to positive infinity. And I'm just going to union those two, okay? To be honest, there's really not a gap in my domain, but there is definitely a gap, so I'm going to kind of leave that so people can see there's something that's happening there. Okay, for my range, what y values are used? Well, my farthest down is negative infinity because of my arrow over here. And then, be careful, I go all the way up to my y value of 0. And it includes that. Then my next y value, I skip and I'm up here at 3. And it includes it. And then I go to positive infinity. Okay, and again, there's a union between those. Okay, so piecewise function, there's usually gaps in it. Not always, but there's often gaps in it. So don't be surprised when you see that. Okay, all right, so I have one more part of this set of notes to go, and it's the different quotient of a function, okay? I can't stress enough for you. This is for calculus, okay? It's going to seem really strange, but we're going to do this so that you get ready for calculus for the difference quotient, okay? So we get this different quotient. As or when you need this on a test or quiz, I will give it to you, but you need to know how to properly work through it, okay? So this difference quotient is what we are using. So it says find and simplify the difference quotient for these given functions. Okay, so what we do is we plug in all of these values. Okay, so we're going to break it apart a little bit. First, I just want to find f of x plus h, okay, because it's different with every function. So let's find that first. So that means in this, wherever I see x, I'm plugging x plus h in. So I get 6x plus 6h plus 1. There's my f of x plus h, okay? Now, if you think about it, that's what I can plug into this part right here. I have my f of x because it is what they started me with, and then I have an h. Okay, so now we're ready to do this whole thing of f of x plus h minus f of x all over h. Okay, so I already found my f of x plus h. I'm going to plug in 6x plus 6h plus 1. Now I'm going to subtract my entire f of x, which was 6x plus 1, all over h. Okay, distributing my negative through. I get 6x plus 6h plus 1 minus 6x minus 1 all over h. Well, when I go to simplify, my 6x and my minus 6x cancel. My positive 1 and my minus 1 cancel. And I'm left with 6h over h, which simplifies to 6. Okay? So my difference quotient ends up equaling 6. Okay? Where's this going? Well, I'm going to tell you right now, derivative means nothing to you today, but someday in calculus it will. Okay? This is where we're going with our difference quotient. All right, let's try this again with a little bit bigger function with a few more terms on it. Okay? And we see, again, we need to find our f of x plus h. It's easier, I find, to do it separate and then join it in. Okay, so I'm going to plug in x plus h everywhere I see an x. So I have negative 3. Plug in x plus h. Plug in x plus h minus 1. Okay, don't forget, when it's squared, I need to FOIL. So it's negative 3 times. When I FOIL x plus h, I'm going to have x squared. I'm going to have two middle terms of xh and an h squared. All right, plus 2 times x plus h minus 1. Ugh. I don't know why. I apparently reached the edge of the screen. Okay, let's distribute what we have. I'll move it over a little bit. I get negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h, and then that minus 1 that went off the screen a little bit earlier. Okay, does anything join? And I'd have to say no. Okay, so we are ready to put and plug into the difference quotient. I'm not going to rewrite that whole difference quotient again, so I put on top the f of x plus h, which is negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h minus 1. And now I'm going to subtract my function, which was negative 3x squared plus 2x minus 1 all over h. Okay. Try not to drop any signs or anything. I'm left with negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h minus 1 plus 3x. Wow, don't ask me why I changed that to a 4. Plus 3x squared minus 2x plus 1 all over h. Okay, things better happen. Yes, negative 3x squared plus 3x squared plus 2x minus 2x minus 1 plus 1. All right, let's see if I can figure out what's left. I have a negative 6xh minus 3h squared plus 2h all over h. Okay. On the top, I can factor out a GCF of h, and I'm left with negative 6x minus 3h plus 2. Of course, I hit the edge again. Just a minute, I don't know which way I want to go on that. I don't know if that'll help me at all. Anyways, I should probably just leave it before I wreck everything. All right, there's a plus 2 over there, all over h. My h's cancel, they divide out. And I'm left with negative 6x minus 3h plus 2. And that's my difference quotient, okay? And for all of them, we should make sure, we always make sure we know h cannot equal 0, right? Because it couldn't be 0 and be in that denominator. So keep in mind it can't equal 0. All right. I'm going to be honest, kind of a hodgepodge of things on these moron functions and their graphs. So a little bit even and odd, a little difference quotient, a little bit of piecewise functions, increasing, decreasing, and stuff. Kind of a lot of little things to remember. It'd be a good idea to practice at least something from every section to make sure what we talked about makes sense. If you have questions, let me know.